Hello students, welcome back again. In this part, we will discuss basic applications involved in the electromagnetic inductions like electric generator, transformer, induction stop and induction coil. And then we will discuss basic characteristics of the transformers, primary coil and secondary coil. So let's start. Let's discuss about applications part involved in the electromagnetic induction. So first point is related to the electric generator. We know that electric generator contains two parts, stator and rotor. And rotor is rotating into that stationary part, rotor. Same phenomena involved with the electric motor. Also we will discuss our induction stove, transformers. So transformer means same phenomena of mutual induction take place. In case of induction stove, here the conservation of energy take place. How? That electric energy is converted into heating energy, and the first part is associated with the electric generator. In electric generator transforms mechanical energy into electric energy, and this is just an AC generator. So first of all we will discuss here the construction part. This is brush connected with the slip rings, and then we have an armature. Armature is a rotatory part, and we called it as stator part, stator, and this is its rotor. Now the main point is that there is some external magnetic field that is in the fixed situation. There is an armature coil that rotates into that magnetic field. So due to the rotation of armature into that stationary magnetic field, some flux is cutting with respect to time t. Due to the cutting of magnetic flux, some EMF is induced, and due to that EMF some current is produced, or some current is induced. Due to that, when that current flows through the coil or the electric resistance like electric bulb, then there is potential drop. Due to that potential drop, there is blinking of bulb. So here we can discuss the axle is rotated by an external force such as falling water or steam. That is a case of turbine. Maybe case of your wind energy, how rotation of wind convert into rotation of wind, that is a phenomenon of mechanical energy causes inducement of electric current, and that current when passing through the resistance there is a potential drop. So point is that these brushes are in contact with the electrical contact with the slip rings as shown over here. Now what is the induced EMF across this? Induced EMF, when the coil is rotated with a constant angular speed omega, the magnetic field vector B and area vector as A of the coil at an instant theta is equal to omega into time t. This is what the angular displacement. Assuming at theta equal to 0 degree and t equal to 0, we found that net magnetic flux produced is equal to BA cos theta, or we can say it as BA cos omega t. Because coil is rotating into that magnetic field, so definitely angle theta will change, and that angle theta would be a function of angular speed multiplied by time t. This time we are interested to know the induced EMF. We can find it by differentiating the flux value. Now on differentiating we are getting E is equal to minus n d phi by dt, and we know that n number of turns of the coil are considered over here, and due to that we are getting EMF as NBA sine of omega t. But we are interested to know only the magnitude, that's why we need to consider the modulus of flux value or EMF value, and this is called as instantaneous value of EMF as it is changing with respect to time t. Now after this we can depict the graph. Means this diagram 1 represents the rotation of coil into the magnetic field. It is given here magnetic field is acted along x direction, and we are considering a rotating coil into that magnetic field. If that coil makes angle theta degree with the magnetic field, we found cos 0 equal to 1. Flux is maximum. When it turns to 90 degree, we find magnetic flux becomes 0 degree. Again it turns to 180 degree, we found that magnetic flux is minimum in that case, and finally come to 270 and 360 degree. For these different values of angle or angular displacement, we depict the graph for induced EMF as well as current. always try to understand, if we draw this graph for induced current, definitely the value of induced current will be something lesser amplitude, would be of lesser amplitude. So we can say this would be the graph for the induced current, and this is the graph for induced current. E naught is the peak value. So already we know that I is equal to the EMF upon resistance R. Resistance R is the obstruction offered like electric bulb or any electric or electronic appliances connected in series across that device. So here we depict variation of EMF with the rotation of the coil. Simply it is a game of, it is mechanical situation of displacement theta. Now, second application involved with this is induction stove. You have seen in many houses like induction cooker. So how that electric energy converts into heating energy. So we can say an AC current in a coil in a stove top produces a changing magnetic field and at the bottom of the metal pan. So we can say this is what a special type of pan is used for this induction cooker that can experience maximum effect of heating energy. Means if we are using iron or any aluminum or any special type of device, because we discussed already concept of eddy currents. So eddy current causes heating loss. Same here, if there is drawback like eddy current produce a wave, that's why we avoid any iron elements, iron copper or any copper or any silver materials as a pan. So we use stainless steel kind of pan for this induction cooker. And what is the concept? The changing magnetic field gives rise to current in the bottom of a pan because it operates on a particular frequency that causes change in the magnetic field, and that magnetic field with that particular area causes flux and definitely heating energy produced. Because of this fan has a resistance, the value of current passing through that resistance causes heat. If the coil in the stove has low resistance, it doesn't get hot, but the pan does. So we try to use a pan of required resistance that the power, or we can say heat dissipated across the device is up to that value. Now an insulated wouldn't heat up an induction of cooker because what we are talking about inducement of current or inducement of EMF. If we are using insulating material, no such phenomena can occur through that. So this is the basic principle of induction stove. Now we will discuss about transformer. We have seen many times transformer focus. To transform, it is here used to transform the power or the voltage from primary to secondary source. So you can see here the primary binding, you can see here the secondary binding. Point is that we want to charge our mobile that requires 12 volt of battery, but the household activities contains 150 to 220 volt, nearly about it. So what we are required, we are in a situation to have 12 volt for our mobile phone. So we need an adapter. That adapter transform higher voltage to lower voltage. Or when there are high tension line, you want lower potential values for the same current, then you use step down transformer. So we need to understand step down, you are decreasing the potential. Step up, you are increasing, you are grading the potential from primary to secondary by changing the number of orientations, number of coils, turns. Now transformer is basically two coils of wire wrapped around each other, around an iron core. So this is an iron core over where we consider two wrapped iron. Now, a transformer is a device for an increasing or decreasing an AC voltage across these primary and secondary. When an AC voltage is applied to the primary, it induces an AC voltage in the secondary. Of course, I told you earlier about induction phenomena in case of mutual inductance. Whenever current is flowing across primary coil, there would be magnetic lines of force, and that magnetic lines of force passing through the area of the secondary one, definitely there would be flux cutting across the second one, and due to that flux cutting with respect to time t, it causes induced EMF and induced current in the secondary coil. So in this way we are getting the effect of induced EMF as well as induced current in the secondary coil, and it depends on the number of turns. Now second, Transformer characteristics. This is very important part. We need to understand, like step up transformer increases the output voltage in the secondary coil, and step down transformer reduces it. Actually, we must understand EMF depends on number of turns and the flux induced. So when we are considering flux phenomena, mutual inductance for two coils, flux is same. Flux in one should be equal to flux in two, but EMF will differ. That EMF will depend on number of turns. So it is necessary to consider number of turns. That's why we set up a relation for primary as well as for secondary. We can see these are the EMF values for primary as well as for secondary. Now we are getting the relationship for primary to secondary. How it depends on primary to secondary. ES upon EP, that is equal to NS upon NP. Means if we want to upgrade the potential, means we are discussing here the case of step up. That's why we need to increase the number of turns in the secondary. Or we want to degrade the potential in case of a step down, we need to reduce the number of turns in the secondary. So this actually happens, and it is just involved in all kind of transformers we are using. Now this is the diagram represent here for transformer. Means we are considering a primary AC source through which current I is flowing. We are calling it as primary current. When this primary current flows through this wrapped wire over this iron part, having number of turns NP, magnetic lines of force will produce. When these magnetic lines of force passes through the coil or through the air core of the secondary coil, we are getting firm flux. Due to that flux cutting, there would be some induced EMF, and that in EMF cause secondary current, and that can be sensed by the resistance we are connecting. Also we can use voltmeter to measure this potential drop across this resistance. The main function is Vp upon Vs. Primary to secondary is equal to primary upon secondary. As we know that flux in 1 can be assumed to be equal to flux in coil 2. That's why we are getting Vp upon Vs is equal to Np upon Ns. And we know that we need to consider current to be same over here. Now, what are the transformer characteristics? Already means in case of step up, we know that secondary is greater than primary, or potential is greater than this one. Similarly, in case of a step down, primary is greater than secondary, or Vp is greater than Vs we have. This is in case of this. Now, energy must be conserved. Of course, energy must be conserved. 100% energy conservation is not possible. Means some energy is just wasted as heat. Or against eddy current. Already we discussed eddy current. The current flows across the metallic part or the conduction part. Means we consider metallic plate, and some current will flows on the surface of this. That's why it produces heat across that device. And we can minimize that eddy currents by laminating a coil. Similarly, energy must be considered, like ratio of current across the coil is inversely proportional to the ratio of number of turns. So Is upon Ip equal to Np upon Ns. So we can set up a relation for current as well as for voltage. So we know that resistance is just equal. That's why Is upon Ip equal to Np upon Ns. This is for current relationship. This is for your voltage relationship. Now, we will discuss in this past losses in transformer. In practice, real transformer are less than 100% efficient, although it is not possible. Are less than means if we want to develop a transformer that can transmit 100% efficiency, it's not possible. So there are some laws, resistive laws, like in the coils which can be reduced by making their cross section large and by using high purity copper. We know that gold is the most conductive, then we have silver, then we have copper, and then aluminum and the silver. But we prefer copper because it is cheap and better for conduction. That's why we are using. So if we use better conduction, definitely the rate of conduction will be good, but somewhat it would not be 100% efficient. Now, second cause is due to eddy currents. We already discussed in the core. Eddy current is always in the core because it contains hard metallic part. That's why, which can be reduced by laminating the core. Laminations reduces the area of the circuits in the core, and so reduces the EMF and current flowing in the core, and energy is lost. So already we discussed heating of the laminating core or heating of the metallic conducting part is due to the eddy currents on the through this, and we can avoid it up to certain value by laminating it. Although we can't reduce eddy currents to zero, it is impossible actually. So because what there, so we can see in every electronic device that get heated up, it is due to the eddy currents. So and this. Now also we have the third part, that is hysteresis loss. So hysteresis loss in the coil is just the magnetization and demagnetization curve for magnetic materials are often a little different, and this means the energy required to magnetize a core which current is decreasing. The difference in energy is lost as a heat in the core. So means hysteresis loss is just related to the residual magnetism behavior. We already discussed magnetic lines, so force passes through the secondary coil also, but it doesn't mean the core's concept of demagnetizes 100% conserved. No, some residual magnetism is also observed that causes hysteresis loss, that cover retentivity and coercitivity in this concept. Also, the last clause we can consider a geometrical design, as well as means if we consider two coils mutual to each other, we can say the passes of lines through the secondary will be maximum. But if we put two coils parallel to each other, we can say it is very typical to get maximum efficiency from this. So we need to consider a good design for transformer like this. So these are the theory section involved with this. Now we will discuss some questions based on this concept. And this question, a coil of metallic wire is kept. A coil of metallic wire is kept stationary in a non-uniform magnetic field, and EMF is induced in the coil or not. We have to check whether this statement is true or false. In the solution part, it is clear written over here, EMF is equal to change of magnetic flux with respect to time t. If we consider n number of turns, we can put n into change in magnetic field upon delta t. Now it is written over here, for induced EMF to develop a coil, the magnetic flux through it must change, but E is equal to A delta B upon delta t, and it is given here non-uniform magnetic field. A coil is coil of metal where wire is kept stationary in this one. So means there is no relative motion. As no relative motion means no cutting in flux. So that is no relative motion. We can say no cutting in magnetic flux, no cutting of magnetic flux. It means we can say EMF is considered to be zero. That's why this statement is false. This is based on the Faraday's laws of experiment. Now, second question is about a coil of inductance 1 Henry. So also we will note down the given values, that L is equal to 1 Henry. Resistance R equal to 100 ohm. Is connected to a battery of EMF. So E is also given at 12 volt. Find the energy stored in the magnetic field of the coil 10 millisecond. So T is equal to 10 millisecond. That is equal to 10 into 10 to the power minus 3 second when it is switched on. So we must understand energy stored across the coil is equal to 1 by 2 Li square. But we must understand whether it is a case of growing of current across the coil or decay of current. So we know that when current is growing, so we can say IT is equal to E, means it is like this, inducting coil, and then we have resistance. So connecting with the battery we have like this. So growing of current across this coil can be expressed as a function of IT, that is equal to E by R into 1 minus E to the power R T by L, T by tau. We can say this relaxation time is equal to L by R or T by tau. On substituting the value of I over here in the main relation, so we get E is equal to 1 by 2 L into E by resistance R, 1 minus E to the power R T by L whole square. Now we will substitute the values like 1 by 2 into 1 into 12 by 10, 1 minus E to the power R is 100 ohm, T is given as 10 into 10 to the power minus 3, L is given as 1 Henry, and square of this value. it would be a mathematical relation, and we are getting it as 144 by 2 into 10 to the power 2 into 10 square r this into 1 minus e to the power, finally that is 1 minus 1 by e, means when we will solve it, already I solved it, that's why I am writing here, that is equal to when we solve it, and the value of e is considered as 2.78. So on substituting this value, we are getting it is approximately 28.8 into 10 to the power minus 3 joule. So we can say that is equal to 28.2 millijoule. So this question is related to the growth of current across the inducting coil connected in series with the resistance. So we when energy across the inducting coil is 1 by 2 Li square at any moment, and time is given, that is at 10 millisecond. In that 10 millisecond, so the growth of current across that inducting coil within that 10 second is equal to E by R 1 minus E to the power RT by L. On substituting the corresponding values by knowing E is equal to 2.78, we are getting 28.8 millijoule is the right answer for this question. So always try to understand wherever you are seeing question based on transient current, growth of current and decay of current in electromagnetic induction. Please try to solve all these questions. In this part, we discuss basic application involved in electromagnetic induction like electric generator, induction stop, induction coils, and basic application or characteristics of the transformer. Now, in the next part, we will discuss questions based on electromagnetic induction. So stay tuned with us.